For billions of years, stars have been born in clouds of dust and gas, lighting galaxies with their glow, shaping worlds and fueling the cycle of life. But nothing lasts forever. One day the stars will stop being born, galaxies will fall silent. In the vast cosmic darkness, each galaxy pulses with the birth and death of countless stars. These stellar nurseries have continued their cycle since the dawn of our universe, painting the cosmos with light and creating the elements that form everything we know. Yet even this grand process must eventually come to an end. As we look deep into space, we're seeing galaxies at different stages of their long lives. Some burst with the blue light of new stars, while others glow with the softer, reddish hue of aging stellar populations. This is the story of how these cosmic islands evolve, how they slowly exhaust their star-forming potential, and what happens when the last stars fade away. Our journey will take us across billions of years, from the vibrant youth of the early universe to its quiet, distant future. We'll witness the processes that drive star formation and those that extinguish it. We'll contemplate what it means for a galaxy to grow quiet, and what might remain when the lights finally go out. Tonight, as you rest beneath your own canopy of stars, imagine the countless galaxies suspended in the void above you. Each one a city of stars, each star a furnace of light and heat. For now, they burn bright, but in the grand cosmic timeline, even they are merely moments, fleeting bursts of brilliance against the eternal dark. The story of galactic evolution is also our story. We are, after all, made of stardust, the very elements forged in stellar cores and scattered by their explosive deaths. To understand the life and death of galaxies is to understand our cosmic heritage, our place in this vast, interconnected universe. Listen to the whispers of distant star systems as they tell their tale of creation and eventual silence. Feel the gentle rhythm of cosmic time as it flows like a river, carrying galaxies from their brilliant youth to their quiet maturity. And perhaps in that quietude, find a certain peace. So settle in as we explore this cosmic twilight together. The gentle fading of galaxies as they run out of stars, a tale of cosmic endings, but also of the incredible persistence of light against the darkness of space and time. To understand why galaxies eventually stop forming stars, we must first understand what stars truly are and how they come to be. At its most fundamental, a star is nature's way of balancing opposing forces. Picture a vast cloud of hydrogen gas drifting in the darkness between stars. This cloud, known as a molecular cloud, might span hundreds of light years across. Within this cloud, gravity works its subtle magic, pulling the individual atoms closer together. As they draw nearer, the cloud begins to fragment into smaller clumps. Gravity continues its patient work, compressing these clumps further and further. As the gas compresses, something remarkable happens. It begins to warm. This is the same principle that makes a bicycle pump warm to the touch when you compress air. But in space, this process occurs on an unimaginable scale. As the temperature rises at the center of these gas clumps, the atoms move faster and faster, colliding with greater energy. When the temperature reaches several million degrees, something extraordinary occurs. Hydrogen atoms begin to fuse together, forming helium. This process, nuclear fusion, releases tremendous energy. The outward pressure from this energy finally balances the inward pull of gravity. A delicate equilibrium is achieved, and a star is born. The newborn star glows with its own light, sometimes blue-white and fierce if it's massive, or perhaps orange-red and gentle if it's smaller. Each star is unique, yet all follow this same basic pattern of birth. Within galaxies, these stellar nurseries appear as beautiful nebulae, vast glowing clouds of gas and dust illuminated by the hot young stars forming within them. The Eagle Nebula, the Orion Nebula, the Carina Nebula. These are cosmic cradles, birthing thousands of stars even as we speak. But what determines whether a galaxy forms stars readily or struggles to create new stellar children? The answer lies in several factors. First and foremost is the availability of gas, particularly cold, dense molecular hydrogen. This is the primary building material of stars, the essential ingredient in the cosmic recipe. Galaxies rich in cool gas form stars vigorously, while those depleted of gas grow quieter. Temperature plays a crucial role as well. Gas must be cold enough to collapse under its own gravity. When gas heats up, the atoms move too quickly to clump together, preventing the initial stages of star formation. This is why some galaxies with plenty of gas might still struggle to form stars. Their gas is simply too warm. Density matters greatly too. Imagine trying to make a snowball from sparse, powdery snow. It's much harder than using tightly packed snow. Similarly, sparse gas takes much longer to collapse and form stars than dense gas. The denser the gas clouds, the more readily they form stars. In the spiral arms of galaxies like our own Milky Way, gas clouds are compressed as they move through these arms, like water piling up before a dam. This compression triggers waves of star formation, creating the beautiful blue strings of young stars we see tracing spiral patterns. Some galaxies experience periods of intense star formation called starbursts. These cosmic fireworks can be triggered by collisions or near misses with other galaxies. As two galaxies interact, their gas clouds slam together, creating ideal conditions for a flurry of new stars. These starburst galaxies shine brilliantly, but like fireworks, their spectacular display is often short-lived. The environment surrounding a galaxy also influences its star-forming capabilities. Galaxies in dense clusters may have their gas stripped away by the pressure of moving through the hot gas that fills the space between cluster galaxies. Like a cyclist feeling the wind tear at their clothing, these galaxies lose their star-forming potential to the harsh, cosmic environment. Beyond all these factors lies the subtle influence of timing. The early universe was rich in pristine hydrogen gas, allowing for vigorous star formation. As the cosmos ages, this original supply of gas diminishes. Galaxies must increasingly rely on recycled gas material expelled from dying stars. Within the stellar nurseries themselves, the process of star formation follows a wondrous pattern. Gas clouds develop filaments and nodes, areas of greater density that attract more matter. Within these nodes, protostars begin to form not yet true stars, but warming collections of gas on the path to stellar birth. Around these protostars, disks of rotating material form. From these protoplanetary disks, planets may eventually coalesce, perhaps rocky worlds like our own Earth, or gas giants like Jupiter. The birth of stars thus contains within it the potential for entire solar systems, for worlds that might one day harbor life. Not all stars form in isolation. Many are born in clusters, families of stars all formed from the same parent cloud. The Pleiades, visible to the naked eye as a small dipper-shaped cluster, represent such a stellar family, siblings born together from the same cosmic womb. The most massive stars in these clusters live fast and die young, their tremendous energy output exhausting their fuel quickly. Before they die, they shine with ultraviolet light so intense it ionizes the surrounding gas, creating glowing bubbles of hot plasma. These massive stars shape their environments, both nurturing and disrupting the birth of their smaller siblings. When stars form, they do not use all available gas. Some is blown away by stellar winds, some remains too diffuse to collapse. This leftover material becomes the medium from which future generations of stars might form. In this way, galaxies maintain their star-forming potential across billions of years, each generation of stars feeding into the next. But like a forest that eventually runs out of seeds, or soil that grows depleted of nutrients, galaxies eventually begin to exhaust their star-forming potential. The raw materials become scarce, or conditions no longer favor the delicate process of stellar birth. The transition is gradual, a slow quieting of the stellar nurseries, a dimming of the bright blue glow of young stars. Regions that once sparkled with new life grow still. The galaxy does not die. Its existing stars continue to shine, but it no longer creates new stellar children. This slow change from active star formation to quiescence marks one of the most significant transitions in a galaxy's long life. It is a change we can observe in progress across the universe, from the vigorously star-forming galaxies of the distant past to the quieter, redder galaxies of more recent cosmic epochs. But the transition occurs over timescales far beyond human lifetimes, hundreds of millions or billions of years. We see it only in snapshots, like watching the seasons change through photographs taken months apart. Yet through these cosmic snapshots, we piece together the long, slow evolution of galaxies as their star-forming potential gradually wanes. What causes this transition? What processes can strip a galaxy of its ability to form new stars? To understand this, we must look deeper into the life cycles of galaxies themselves, how they grow, evolve, and eventually fall silent. And in time, the fuel begins to run dry. When we consider a galaxy that has ceased forming stars, we're typically thinking in terms of human or even cosmic timescales, billions of years, perhaps tens of billions. But what happens in the truly distant future, when even the longest-lived stars begin to fade? What becomes of galaxies when all their fuel is truly gone? To answer these questions, we must extend our gaze far beyond the current age of the universe, into a remote future that staggers the imagination. We must think in terms not of billions, but trillions of years, durations so vast they dwarf the current age of the cosmos. Let us begin by examining the timeline for star formation to completely cease throughout the universe. The cosmic story of star formation has already passed its most vigorous chapter. The peak of star formation in our universe occurred roughly 10 billion years ago, when stars were being born at rates far higher than today. Since then, the overall cosmic star formation rate has been in steady decline. As we look toward the future, this decline will continue. Studies of the remaining gas content in galaxies, coupled with current star formation rates, suggest that most galaxies will exhaust their star-forming potential within the next trillion years, about 100 times the current age of the universe. Some galaxies will burn out much sooner. Many massive elliptical galaxies have already largely ceased star formation, and within a few billion years, they'll produce their last new stars. Our own Milky Way, should it not receive significant gas infusions, will likely exhaust its star-forming capabilities within about 5 billion years, roughly when our Sun reaches the end of its main sequence life. Other galaxies, particularly small, isolated systems with large gas reserves, may continue forming stars at modest rates for much longer, perhaps tens or even hundreds of billions of years. But eventually, even these stellar nurseries will close their doors. Several factors drive this long-term cessation of star formation. The most straightforward is simply the depletion of gas reserves. Stars form from interstellar gas, primarily hydrogen and helium, and this gas is not infinite. Every star that forms consumes a portion of this limited resource. While some gas is returned to the interstellar medium through stellar winds and explosions, much becomes locked away in long-lived stars and stellar remnants. Over vast timescales, the reservoir of free gas gradually diminishes, making new star formation increasingly rare. The expansion of the universe compounds this problem. As space expands, the density of matter decreases, making it harder for gas to reach the densities necessary for gravitational collapse and star formation. Galaxies become increasingly isolated from one another, cutting off the possibility of gas replenishment through mergers or accretion. Additionally, the gas that remains often becomes harder to convert into stars. As galaxies age, their gas tends to heat up through various energetic processes, supernova explosions, radiation from existing stars, and the gravitational energy released as gas falls into galactic potentials. This warmer gas resists the compression necessary for star formation. By about 1 trillion years from now, traditional star formation as we understand it will have largely ceased throughout the observable universe. The great stellar factories that once illuminated the cosmos will have shut down, their raw materials exhausted, their machinery stilled. But this doesn't mean galaxies will be empty or dark. Far from it. The stars already formed will continue to shine, many of them for extraordinarily long periods. When we say a galaxy has run out of stars, we don't mean its existing stars have vanished, only that it no longer forms new ones. Let's consider what galaxies will look like in this far future, when star formation has completely ceased. Their appearance will be dramatically different from the galaxies we observe today. The brilliant blue regions of active star formation will be long gone. The delicate spiral arms that trace recent star formation in galaxies like our Milky Way will have faded into obscurity. What remains will be collections of stars dominated by the longest-lived stellar types. Most massive stars, the brilliant but short-lived giants that dominate the light of star-forming regions, will have long since exploded as supernovae. Stars similar to our Sun will have evolved through their red giant phases, shed their outer layers as planetary nebulae, and shrunk to become white dwarfs. The stellar population will be dominated by red dwarf stars. the small, cool, efficient stars that make up the majority of all stars even today. These cosmic misers burn their hydrogen so slowly and efficiently that they can shine for trillions of years. In the far future, they will be the last main sequence stars still burning, the final embers of stellar fire in an increasingly cold universe. Accompanying these red dwarfs will be a growing population of stellar remnants, the end products of stellar evolution. White dwarfs, the dense cooling cores left behind by sun-like stars, will be abundant. These strange objects, roughly Earth-sized but containing up to 1.4 solar masses of matter, don't generate energy through fusion. Instead, they simply cool, very gradually radiating away their residual heat. A smaller but significant population of neutron stars will also persist, the superdense remnants of more massive stars. Like white dwarfs, these objects no longer generate energy through fusion. They simply cool, their intense surface temperatures of millions of degrees gradually decreasing over billions and trillions of years. Black holes too will be common, both the stellar mass black holes formed from the most massive stars and the supermassive black holes that reside at the centers of most galaxies. These objects will continue to grow slowly by consuming nearby stars and gas, though this growth will become increasingly limited as galaxies age and material becomes scarcer. The overall picture is one of a galaxy gradually transitioning from a dynamic, evolving system to a more static collection of aging stellar objects. The vibrant blue-white light of young stars will give way entirely to the soft red glow of aging red dwarfs, punctuated by the faint light of cooling white dwarfs. But will galaxies ever truly be empty? The answer depends on what we mean by empty. If we mean devoid of stars altogether, then no, at least not for an unimaginably long time. The smallest red dwarf stars may shine feebly for up to 20 trillion years. That's about 2,000 times longer than the current age of the universe. However, if by empty we mean devoid of active, fusion-powered stars, then yes, galaxies will eventually reach this state. After the last red dwarf exhausts its hydrogen fuel, there will be no more nuclear fusion occurring in main sequence stars. The stellar fires that have lit the cosmos since its early days will have gone out. What remains after this point, in the far distant future, perhaps 20 trillion years from now, will be a collection of cooling stellar remnants. White dwarfs will slowly radiate away their heat, their initially white-hot surfaces gradually cooling to yellow, then red, then infrared, and eventually to the background temperature of the universe. This cooling phase marks the transition to what cosmologists call the degenerate era, a period characterized by the prevalence of degenerate stellar remnants rather than active stars. During this era, galaxies will be increasingly dark in visible light, though they would still be detectable in infrared and radio wavelengths. As white dwarfs cool below about 3000 Kelvin, a process that takes hundreds of billions to trillions of years, they become black dwarfs, stellar corpses that no longer emit significant visible light. These objects, Earth-sized spheres of carbon and oxygen with the mass of a star, will be among the most common objects in future galaxies. The cooling process for these stellar remnants is not uniform. More massive white dwarfs and neutron stars cool more slowly than less massive ones. This creates an era where the only visible objects in galaxies may be the most massive stellar remnants, the last faint points of light in an increasingly dark cosmic landscape. Eventually, even these last visible objects will fade from view. The galaxy will still exist as a gravitationally bound collection of black dwarfs, neutron stars, and black holes, but it will be invisible to eyes like ours that evolved to detect visible light. The light show that has illuminated the cosmos for nearly 14 billion years will have finally ended. But even in this dark future, occasional brief flashes of light may occur. When stellar remnants pass close to each other, an increasingly rare event in the expanding, aging universe, they can generate various energetic phenomena. White dwarf collisions might briefly reignite nuclear fusion in their outer layers. Neutron star mergers could produce short gamma-ray bursts. Black hole mergers would release gravitational waves and potentially electromagnetic radiation if material is present to be heated. This slow dimming of galactic light represents one of the most profound transitions in cosmic evolution. The end of the stelliferous era, when stars dominated the universe, and the beginning of the degenerate era, when stellar remnants take center stage. It marks the closure of a chapter in cosmic history that has lasted since the first stars formed, just a few 100 million years after the Big Bang. No new stars, just a collection of cooling embers drifting quietly through time. In the vast cosmic timeline, our current epoch, the age of stars, is merely a brief chapter. Though it seems eternal to us, the era of stellar light is fleeting against the backdrop of deep time. Eventually, star formation will cease throughout the universe, and one by one, existing stars will exhaust their fuel and fade away. But which stars will be the last to shine? What final points of light will flicker in the darkening cosmos before the stellar age comes to its ultimate end? The answer lies in understanding which stars live the longest. A star's lifespan is inversely related to its mass. The more massive a star, the shorter its life. This counterintuitive relationship stems from the intense pressure and temperature at the cores of massive stars, which cause them to burn through their hydrogen fuel at a dramatically accelerated rate. The most massive stars, blue giants, with 30 or more times the mass of our Sun, exhaust their fuel in just a few million years. Stars with the mass of our Sun shine steadily for about 10 billion years, but the smallest stars, the dim red dwarfs, burn their fuel with extraordinary efficiency, allowing them to shine for trillions of years. These red dwarfs will be the last normal stars in the universe. With masses between roughly 8% and 50% that of our Sun, they are the most common type of star in the cosmos, though their faintness makes them difficult to observe. Cool and dim compared to stars like our Sun, they compensate for their low energy output with remarkable longevity. The secret to their extended lifespans lies in their internal structure. Unlike more massive stars, red dwarfs are convective throughout. This means the hydrogen fuel is continuously circulated from the surface to the core, allowing nearly all of the star's hydrogen to be used for fusion rather than just the core material. Additionally, the fusion reactions in red dwarfs occur more slowly and at lower temperatures than in larger stars. This slower burn rate means they consume their fuel at a glacial pace compared to their more massive cousins. The result is astonishing longevity. A red dwarf with about 20% of the Sun's mass might shine for about 2 trillion years, roughly 200 times the current age of the universe. The smallest viable stars, those with about 8% of the Sun's mass, just above the boundary where fusion can be sustained, may continue shining for up to 20 trillion years. As the universe ages and evolves, these humble red dwarfs will become increasingly dominant. By 1 trillion years from now, about 70 times the current age of the universe, essentially all star formation will have ceased. The massive, brilliant stars that once defined cosmic structures will be long gone. Even sun-like stars will have exhausted their fuel, swelled into red giants, shed their outer layers, and collapsed into cooling white dwarfs. Only the red dwarfs will remain as active, fusion-powered stars. These cosmic embers will continue to provide a faint illumination to an otherwise darkening universe. Galaxies will still be visible, but they will appear as diffuse red collections of these dim stars, quite unlike the vibrant spiral and elliptical structures we observe today. What would these last stars look like up close? With surface temperatures of around 2,700 degrees Celsius, less than half that of our Sun, they would glow with a deep red light. Their size would be modest, roughly 1/10 the diameter of our Sun, similar to or slightly larger than Jupiter. Despite burning for trillions of years, they would have changed very little in appearance since their formation, as their low mass makes them remarkably stable over cosmic timescales. Any planets orbiting these final stars would need to huddle close to receive warmth and light. The habitable zone would be just a narrow band extremely close to the star. These planets would likely be tidally locked, with one side perpetually facing their dim sun, creating a stark division between a warm, illuminated hemisphere and a frigid, dark one. In the vast cosmic timeline, our current epoch, the age of stars, is merely a brief chapter. Though it seems eternal to us, the era of stellar light is fleeting against the backdrop of deep time. Eventually, star formation will cease throughout the universe, and one by one, existing stars will exhaust their fuel and fade away. But which stars will be the last to shine? What final points of light will flicker in the darkening cosmos before the stellar age comes to its ultimate end? The answer lies in understanding which stars live the longest. A star's lifespan is inversely related to its mass. The more massive a star, the shorter its life. This counterintuitive relationship stems from the intense pressure and temperature at the cores of massive stars, which cause them to burn through their hydrogen fuel at a dramatically accelerated rate. The most massive stars, blue giants, with 30 or more times the mass of our Sun, exhaust their fuel in just a few million years. Stars with the mass of our Sun shine steadily for about 10 billion years, but the smallest stars, the dim red dwarfs, burn their fuel with extraordinary efficiency, allowing them to shine for trillions of years. These red dwarfs will be the last normal stars in the universe. With masses between roughly 8% and 50% that of our Sun, they are the most common type of star in the cosmos, though their faintness makes them difficult to observe. Cool and dim compared to stars like our Sun, they compensate for their low energy output with remarkable longevity. The secret to their extended lifespans lies in their internal structure. Unlike more massive stars, red dwarfs are convective throughout. This means the hydrogen fuel is continuously circulated from the surface to the core, allowing nearly all of the star's hydrogen to be used for fusion rather than just the core material. Additionally, the fusion reactions in red dwarfs occur more slowly and at lower temperatures than in larger stars. This slower burn rate means they consume their fuel at a glacial pace compared to their more massive cousins. The result is astonishing longevity. A red dwarf with about 20% of the Sun's mass might shine for about 2 trillion years, roughly 200 times the current age of the universe. The smallest viable stars, those with about 8% of the Sun's mass, just above the boundary where fusion can be sustained, may continue shining for up to 20 trillion years. As the universe ages and evolves, these humble red dwarfs will become increasingly dominant. By 1 trillion years from now, about 70 times the current age of the universe, essentially all star formation will have ceased. The massive, brilliant stars that once defined cosmic structures will be long gone. Even Sun-like stars will have exhausted their fuel, swelled into red giants, shed their outer layers, and collapsed into cooling white dwarfs. Only the red dwarfs will remain as active, fusion-powered stars. These cosmic embers will continue to provide a faint illumination to an otherwise darkening universe. Galaxies will still be visible, but they will appear as diffuse red collections of these dim stars, quite unlike the vibrant spiral and elliptical structures we observe today. What would these last stars look like up close? With surface temperatures of around 2,700 degrees Celsius, less than half that of our Sun, they would glow with a deep red light. Their size would be modest, roughly 1/10 the diameter of our Sun, similar to or slightly larger than Jupiter. Despite burning for trillions of years, they would have changed very little in appearance since their formation, as their low mass makes them remarkably stable over cosmic timescales. Any planets orbiting these final stars would need to huddle close to receive warmth and light. The habitable zone would be just a narrow band extremely close to the star. These planets would likely be tidally locked, with one side perpetually facing their dim Sun, creating a stark division between a warm, illuminated hemisphere and a frigid, dark one. As fascinating as it is to imagine these last stellar systems, their ultimate fate is inevitable. Even the most efficient stars cannot burn forever. After trillions of years of steady fusion, the last red dwarfs will finally exhaust their hydrogen fuel. Unlike more massive stars, they won't experience a dramatic red giant phase. Instead, these low-mass stars will gradually grow hotter and slightly smaller as hydrogen becomes scarce in their cores. According to current models, these dying red dwarfs will briefly increase in luminosity and temperature, potentially becoming blue dwarfs for a relatively short period, a final, slightly brighter chapter before the end of their long lives. Eventually, fusion reactions will cease altogether. Without the outward pressure of fusion to counteract gravity, these stellar remnants will contract into white dwarfs, dense, Earth-sized objects, composed primarily of degenerate matter. These white dwarfs, the remnants of the last stars, will begin the long process of cooling. Initially hot enough to glow with a faint white or yellow light, they will gradually fade to orange, then red, then infrared, and eventually become cold, dark objects, sometimes called black dwarfs. The transition from the last red dwarf to its white dwarf stage marks the end of the stelliferous era, the age of stars that began just a few 100 million years after the Big Bang and lasted for roughly 20 trillion years. It represents the final extinguishing of the nuclear fires that have illuminated the cosmos throughout its most vibrant period. Imagine for a moment the very last star in the universe, a tiny red dwarf, perhaps in what was once a massive galaxy, now mostly empty as stars, have been gravitationally ejected over trillions of years. This final stellar ember, burning alone in the vastness, represents the conclusion of a cosmic process that began billions of years before Earth even formed. For trillions of years, this star has steadily fused hydrogen into helium, its faint red glow illuminating perhaps a system of ancient planets. And then, after an unimaginably long but still finite lifetime, this final star exhausts its fuel. Its fusion reactions sputter and cease. With this transition, the age of stars comes to its definitive end. In a very real sense, the death of the last red dwarf stars represents the end of the universe as we would recognize it. The cosmos transitions from a place of light and energy to one of darkness and dissipation. The nuclear furnaces that have defined the universe throughout human existence finally go cold, leaving behind only their cooling remains. Yet there is a certain poetry in this cosmic timeline. The smallest, humblest stars, those that shine so faintly we can barely see them from Earth without powerful telescopes, turn out to be the most enduring. While their more massive, luminous cousins burn brightly but briefly, these cosmic embers maintain their steady glow for an expanse of time that dwarfs our comprehension. In the farthest future, only the faintest stars will glow, tiny flames in an ocean of dark. When the last red dwarf star finally exhausts its fuel and ceases fusion, approximately 20 trillion years from now, the universe will enter a fundamentally different epoch. Cosmologists call this new phase the degenerate era, a time when the cosmos is no longer dominated by active, fusion-powered stars, but by their cold, dense remnants. The term degenerate refers to degenerate matter, a state where quantum mechanical effects become important on a macroscopic scale. In degenerate matter, particles are packed so closely together that fundamental quantum principles prevent further compression. This creates objects with extraordinary density, remnants that are the final resting states of once brilliant stars. After star formation has ceased and all stars have exhausted their fuel, three main types of stellar remnants will populate the universe: white dwarfs, neutron stars, and black holes. Each represents a different endpoint in stellar evolution, determined primarily by the original star's mass. White dwarfs will be the most common stellar remnants, as they are the end products of low to medium mass stars which themselves make up the majority of all stars. Our own sun will eventually become a white dwarf, as will all stars with initial masses up to about 8 times that of the sun. These objects are remarkably dense. A typical white dwarf packs a mass comparable to our sun into a volume roughly the size of Earth. When first formed, white dwarfs are extremely hot, with surface temperatures exceeding 20,000 degrees Celsius. But since they no longer generate energy through fusion, they have no way to replenish this heat as it radiates away. Thus begins an extraordinarily long cooling process, where these stellar remnants gradually fade from white-hot to yellow, then red, then invisible infrared, and eventually to cold, dark objects sometimes called black dwarfs. This cooling process spans an almost unimaginable time frame. A typical white dwarf takes hundreds of billions of years to cool to the point where it no longer emits visible light. To reach the theoretical black dwarf state, where it approaches the background temperature of the universe, requires timescales in the range of hundreds of trillions to quadrillions of years. Stars with initial masses between roughly 8 and 20 times that of our sun leave behind neutron stars, objects even denser than white dwarfs. In a neutron star, the mass of 1 to 3 suns is compressed into a sphere just 20 kilometers across. The properties of neutron stars are extreme by any standard. Their surface gravity is about 100 billion times stronger than Earth's, and they typically rotate at incredible speeds, sometimes completing a revolution in just milliseconds. The most massive stars, those with initial masses greater than about 20 times our sun, leave behind black holes. Unlike white dwarfs and neutron stars, black holes are not stabilized by any form of degeneracy pressure. The gravitational force in these objects is so intense that no known physical process can prevent complete collapse, creating a singularity where matter is compressed to infinite density and space-time is dramatically curved. These three types of degenerate objects, white dwarfs, neutron stars, and black holes, will dominate the cosmic landscape during the degenerate era. Galaxies will still exist as gravitationally bound collections of these remnants, but they will be much darker, more diffuse, and structurally different from the galaxies we observe today. Over the immense timespan of the degenerate era, even these seemingly static remnants will undergo further evolution. Through complex gravitational interactions, some stellar remnants will gain enough energy to escape their host galaxies entirely, becoming intergalactic wanderers in the vast cosmic void. The most massive remnants, particularly black holes, tend to sink toward galactic centers, while lighter objects are more likely to be ejected. Another important process during this era is the merger of stellar remnants through gravitational radiation. When two compact objects orbit each other closely, they emit gravitational waves that cause them to spiral gradually towards each other until they eventually merge. Such mergers can create brief but energetic events, temporarily illuminating the otherwise dark degenerate era. When two white dwarfs merge, if their combined mass exceeds about 1.4 solar masses, the result may be a type Ia supernova, a brilliant explosion visible across vast distances. Neutron star mergers create even more energetic events, potentially including short gamma-ray bursts. Black hole mergers release tremendous energy in the form of gravitational waves. These merger events will become increasingly rare as the universe ages and expands. The vast distances between objects will make close encounters progressively less common, and the brightest events will eventually cease altogether. According to some theoretical models in particle physics, protons, which make up much of the ordinary matter in the universe, may not be truly stable. Instead, they might decay with extremely long half-lives, perhaps around 10 to the power of 36 years. If proton decay occurs, white dwarfs and neutron stars would gradually lose mass and change composition as their constituent particles decay. Black holes would also evolve during this era through a process predicted by Stephen Hawking. According to quantum mechanics, black holes should emit a very faint form of radiation, aptly named Hawking radiation. This process causes black holes to lose mass extremely slowly, with smaller black holes evaporating faster than larger ones. For stellar mass black holes, the evaporation timescale is around 10 to the power of 67 years, a duration so vast it dwarfs the current age of the universe by a factor of 10 to the power of 57. Supermassive black holes would last even longer. The universe during this era would be unrecognizable to human eyes. Without the bright beacons of fusion-powered stars, the cosmic landscape would be primarily visible in infrared, radio, and gravitational waves rather than visible light. The few sources of visible light, hot white dwarfs, matter heated by accretion onto black holes, or rare merger events, would be isolated pinpricks against a vast cosmic darkness. Yet even in this seemingly bleak future, the underlying physics remains as elegant and precise as ever. The degenerate era represents not so much an end as a transition from a universe dominated by active, energy-generating processes to one characterized by the slow dissipation of existing energy. What remains is not silence but stillness, echoes of stars that once were. As the stars fade like dying embers across the cosmos, a new era of dominance quietly emerges. The universe, once ablaze with the birth of countless stars, gradually surrenders to a different master, black holes. In these twilight ages of the cosmos, black holes become the primary objects shaping what remains of galactic structure. The process unfolds with the patience of eternity. Massive stars have long since exploded as supernovae, neutron stars have cooled, and white dwarfs have dimmed to near invisibility. What remains are the hungry voids, the places where space and time fold inward upon themselves. Within each aging galaxy, a remarkable transformation takes place. The stellar remnants, white dwarfs, neutron stars, and stellar mass black holes begin a slow gravitational dance. Over unimaginable timescales, these objects interact, transferring momentum, exchanging orbits. With each passing trillion years, more and more matter drifts toward the galactic center where the supermassive black hole waits. This process, dynamic friction, ensures that galaxy cores will eventually collapse inward. Imagine countless dead stars spiraling slowly toward the center, like autumn leaves caught in a gentle whirlpool. The supermassive black holes at galactic centers, once millions or billions of times the mass of our Sun, grow even larger as they consume the remnants of what once were vibrant stellar populations. The Milky Way's central black hole, Sagittarius, a star, currently about 4 million times the mass of our Sun, might eventually grow to contain much of the mass of the inner galaxy. Similar processes unfold in Andromeda, in Triangulum, in distant galaxies whose names we have never known. Not all stellar remnants fall inward, however. Gravitational encounters become increasingly chaotic over time. Like billiard balls colliding on a cosmic table, some stars receive gravitational kicks powerful enough to eject them entirely from their galaxies. These wanderers, frozen white dwarfs, ancient neutron stars, and stellar black holes, are cast into intergalactic space, drifting between the fading islands of light. Rogue black holes become particularly common during this era. Freed from their galactic homes, they wander through the darkness between galaxies. Some travel alone, others may have captured a small family of dead stars that orbit them like ghostly companions. These nomads cross the vast emptiness at thousands of kilometers per hour, occasionally passing near other rogue objects, perhaps altering each other's courses through brief gravitational interactions before continuing their endless journey. Meanwhile, galaxy mergers, events that once triggered spectacular bursts of star formation, now simply combine their black hole populations. When two galaxies merge in this distant era, their supermassive black holes spiral toward each other. The dance can take billions of years, but eventually they merge in a final embrace, sending ripples of gravitational waves across the fabric of space-time, perhaps the last magnificent events in an increasingly quiet universe. These mergers create even more massive black holes. In some cases, the merged black hole may be ejected from its galaxy entirely due to recoil effects, becoming an intergalactic wanderer of almost unimaginable mass. Within this emerging darkness, there exists a strange hierarchy. Stellar mass black holes, those left behind by collapsed stars, range from a few to perhaps 100 times the mass of the Sun. Intermediate black holes might reach thousands or tens of thousands of solar masses, and the supermassive monsters at galactic centers could eventually grow to contain billions or even trillions of solar masses as they consume everything that falls within their gravitational reach. Yet even in this era of black hole dominance, the universe maintains a peculiar order. Black holes aren't truly hungry in the way we might imagine. They don't chase down matter, they simply wait for it to cross their event horizon, that invisible boundary from which nothing, not even light, can escape. Most of the universe remains empty space, with these black objects as islands of intense gravity in a sea of increasing darkness. The most massive black holes shine, in a sense, as they occasionally consume matter, perhaps a rogue planet or dead star that strays too close. The material forms an accretion disk, heating to millions of degrees before disappearing forever. These brief flashes of high-energy radiation become the primary sources of light in the far future universe, rare, sudden, and quickly extinguished. Between these feeding events, even the most massive black holes simply wait, their presence marked only by their gravitational influence on space-time itself. They curve the fabric of reality around them, creating invisible wells that occasionally capture passing objects, slowly adding to their mass over the vast stretches of time. In this way, all movement, all matter, all that remains of the once vibrant cosmic web, gradually falls inward, toward these points of no return. The universe slowly organizes itself around these centers of gravity, these monuments to collapsed matter. Where once galaxies were defined by their brilliant stars, they now exist primarily as collections of black holes in various stages of merger. The observable universe transitions from a place of light and creation to a domain of darkness and consumption. The black holes themselves are not evil or malevolent, they simply are. They represent the natural progression of matter and energy over timescales far beyond human comprehension. In their patient gravity, they embody the universe's slow march towards simplification. And yet, even this era of black hole dominance is not the final chapter in the cosmic story. For as matter continues to fall into black holes, as the dance of gravity continues across eons, the universe prepares for yet another transformation. another phase in its endless evolution through time, slowly falling inward into the blackness. Time stretches beyond imagination as we enter the degenerate era, a cosmic epoch so distant that the numbers themselves become almost meaningless. This phase begins roughly 10 to the 40th power years from now, a time span so vast that it makes the current age of the universe seem like the briefest moment. By this unimaginable future, the universe has transformed into something our ancestors would barely recognize. The once brilliant tapestry of galaxies has faded. No new stars ignite the darkness. The stellar nurseries, those magnificent nebulae where stars once formed, have long since dispersed or been consumed. What remains are the remnants of a universe that once teemed with light and energy. The degenerate era earns its name from the objects that dominate this age, degenerate matter. These are the corpses of stars, compressed into states of matter unlike anything we experience in our daily lives. White dwarfs, the carbon and oxygen cores of stars like our Sun, have cooled to become black dwarfs, radiating no visible light, their temperatures barely above absolute zero. These dark spheres, roughly the size of Earth but containing the mass of stars, drift silently through the void. Neutron stars, once the spinning lighthouses of the cosmos, have also cooled and darkened. Their rotations slowed over trillions of years, their magnetic fields weakened, their surfaces now cold and still. These incredibly dense spheres, just kilometers across yet more massive than our Sun, represent matter compressed to the density of an atomic nucleus. And of course, the black holes remain, having grown larger through accretion and mergers. In this era, they rarely feed, as most matter has either fallen into them already or been ejected to the far reaches of the expanding universe. The most extraordinary aspect of this degenerate era is not what happens, but how rarely anything happens at all. Events become increasingly scarce. In the early universe, stars exploded as supernovae regularly, galaxies collided, and black holes devoured stars in spectacular displays. But now, in this far future, an event as simple as two objects passing near each other might occur once every trillion years in a given region of space. This slowing of cosmic activity reflects the continued expansion of the universe. The cosmic horizons have stretched so far that most objects are now effectively isolated from one another. Gravity, that invisible force that once bound galaxies together, can no longer bridge the expanding gaps between them. Each degenerate object, each black dwarf, neutron star, or black hole exists in growing isolation. Yet even in this quietude, physical processes continue, albeit at glacial rates. One of the most significant is proton decay. According to some theories of particle physics, protons, the building blocks of atomic nuclei, are not truly stable. Over unfathomably long timescales, perhaps 10 to the 36th power years, protons may spontaneously decay into lighter particles. If proton decay occurs, then even the seemingly stable degenerate objects slowly dissolve. The black dwarfs, those cold, dead remnants of stars, would gradually lose mass, atom by atom, as their protons decay. Over periods of time longer than 10 to the 40th power years, these stellar corpses would slowly evaporate, releasing tiny amounts of energy with each decay. This process represents entropy at work on the grandest scale. Entropy, the tendency for organized systems to become disorganized over time, reaches toward its maximum in this era. Complex structures break down into simpler ones. Ordered systems become disordered. The universe moves inexorably toward its simplest possible state. Occasionally, rare events punctuate this slow dissolution. Perhaps once every 10 to the 50th power years, a black dwarf might collide with a neutron star or another black dwarf. These collisions, happening at speeds of hundreds of kilometers per hour, briefly illuminate the darkness as gravitational energy converts to heat. For a moment, light returns to the universe before fading once more into the endless night. Even more rarely, quantum tunneling events might occur within black dwarfs. Quantum tunneling, a process where particles pass through barriers they classically shouldn't be able to penetrate, could occasionally trigger nuclear fusion in the cores of these cold objects. These quantum flashes would be extraordinarily rare, perhaps happening once every 10 to the 60th power years or more. Black holes, meanwhile, experience a profound transformation of their own. According to the work of physicist Stephen Hawking, Black holes aren't truly black forever. Through a quantum process now known as Hawking radiation, black holes slowly emit particles and lose mass. For stellar mass black holes, this evaporation takes roughly 10 to the 67th power years, a time span that dwarfs even the already unimaginable age of the degenerate era. For the supermassive black holes that once anchored galaxies, the process takes even longer, perhaps 10 to the 100th power years. These objects, the last massive structures in the universe, slowly radiate away their enormous mass, growing hotter as they become smaller until they finally explode in a last burst of radiation. This glacial march toward heat death, the state where energy is distributed so evenly throughout the cosmos that no work can be performed, defines the degenerate era. The universe grows ever colder, ever darker, ever more spread out. The gaps between objects widen as cosmic expansion continues. Entropy approaches its maximum. What makes this era particularly poignant is the contrast with the universe's youth, where once energy flowed freely, where stars burned bright and galaxies swirled in cosmic dances, now exists only the occasional flash amid endless darkness. Where complex structures once formed spontaneously, now even the simplest structures gradually unravel. Yet there remains a kind of serene beauty in this cosmic twilight. The processes that unfold during the degenerate era happen with a patience that transcends human understanding. Time itself seems to stretch and slow, as though the universe draws each moment out into eternity. For any hypothetical observer in this distant future, the universe would appear almost entirely dark. The cosmic microwave background, that faint afterglow of the Big Bang, has long since redshifted beyond detectability. The stars have gone out, the galaxies have dispersed, even most black holes have evaporated. What remains is primarily darkness, punctuated by the faintest possible events. A proton decay here, a quantum fluctuation there. In this way, the degenerate era represents a universe winding down, its energy spent, its matter dispersed or degraded. But the colors have faded. Time now is the only thing that moves. As we drift through the darkened cosmos of the far future, a question emerges from the silence. Is this truly the end? Will the universe remain forever in darkness? Or might there be a rebirth of light and energy somewhere in the unimaginable future? The conventional understanding of cosmic evolution suggests a one-way journey toward disorder. Stars burn out, matter decays, and energy dissipates across the ever-expanding void. Yet throughout scientific history, our understanding has been continually revised as we peer deeper into the cosmos. Perhaps the story of existence has chapters we cannot yet comprehend. Some theoretical physicists have proposed models where our universe exists in a closed loop of cosmic time, though current observations suggest this scenario is highly unlikely. In these speculative models, the universe might eventually stop expanding and begin contracting, pulling all matter back toward a point of incredible density and temperature. This big crunch could potentially lead to another Big Bang, reigniting the cosmic fires and beginning the cycle anew. But the evidence we currently possess points in a different direction. The expansion of the universe appears to be accelerating, driven by the mysterious force we call dark energy. If this acceleration continues, the universe will not contract, but will expand forever, growing increasingly cold and diffuse, seemingly precluding any natural rekindling of cosmic fires. Yet even in this scenario of eternal expansion, certain theoretical possibilities remain. Quantum physics, that strange realm of subatomic behavior, offers intriguing glimpses of potential renewal, though in ways far removed from the birth of traditional stars and galaxies. Consider the black holes that dominate the degenerate era. Through Hawking radiation, these cosmic devourers slowly evaporate, releasing energy back into the universe. For the largest supermassive black holes, this process might take 10 to the 100th power years, a time span that makes the current age of the universe seem like the merest blink. But eventually, even these titans would dissolve completely. As black holes evaporate, they grow hotter, releasing more energy. In their final moments, they explode in brief flashes of radiation, the last concentrated bursts of energy in an otherwise cold cosmos. These explosions scatter particles across the expanding void, creating momentary oases of energy in the desert of the far future universe. Quantum fluctuations offer another possible source of renewal. According to quantum field theory, even the vacuum of space isn't truly empty. but continuously bubbles with virtual particles popping in and out of existence. Over vast timescales, these fluctuations might occasionally align to produce significant energy concentrations, brief candles in the cosmic night. Some theoretical models suggest the possibility of vacuum decay, a phase transition where the quantum vacuum of our universe tunnels to a lower energy state. This would create an expanding bubble of altered physical laws that spreads at the speed of light through the existing universe. While this would effectively end our universe as we know it, it would also represent a kind of rebirth, though into a form we cannot predict or imagine. Perhaps the most speculative possibility comes from certain interpretations of string theory and quantum gravity, the idea of baby universes. In these models, quantum fluctuations in black holes or in the vacuum itself might occasionally spawn entirely new universes, connected to our own through wormholes or existing in separate space-time manifolds. While our universe continues its slow fade, these offspring might carry the torch of creation forward. These possibilities highlight an important truth about the cosmos. Our understanding is limited by both our observations and our theories. The universe has surprised us before, revealing phenomena our ancestors could never have predicted. Perhaps the far future holds surprises we cannot yet conceive. The concept of cosmic rebirth appears across human cultures and mythologies. From the phoenix rising from ashes to the endless cycles of creation and destruction in Hindu cosmology, the idea of renewal after ending resonates deeply with the human spirit. Science now offers us its own versions of these ancient stories, grounded in mathematics and observation, but no less awe-inspiring. Even if our universe never reignites in any conventional sense, the matter and energy that comprise it never truly disappear. Energy changes form but cannot be destroyed. The atoms in your body were forged in ancient stars. The light that travels across the cosmos carries information about events billions of years past. In this sense, nothing is ever truly lost, only transformed. As we contemplate these possibilities, we find ourselves at the edge of knowledge, where science begins to touch the philosophical and even the spiritual. The universe we observe with our telescopes and instruments extends vastly beyond our direct experience, and the timeframes we've discussed in this journey extend even further beyond our intuitive grasp. What matters, perhaps, is not whether the universe will literally reignite, but what the question itself illuminates about our place in the cosmos. We are conscious beings in a universe vast enough to contain black holes and galaxies, yet precise enough to form the delicate structures of life. We exist in a moment when stars still shine and energy flows freely, a moment precious for its very transience. The far future may hold darkness or renewal or something we cannot yet imagine. But in contemplating these distant possibilities, we gain perspective on our brief moment in cosmic time, a perspective that can fill us with both humility and wonder, of photons fading into the void. We have journeyed far, you and I, through spiraling galaxies and stellar nurseries, through the death of stars and the dominance of black holes, through timescales that stretch the very fabric of imagination. And now we find ourselves here, in the quiet contemplation of cosmic twilight. There is a certain peace in understanding the finite nature of all things. The stars that shine so brilliantly above us on clear nights are not eternal. The galaxies that swirl through the darkness, each containing billions of stars, will one day grow quiet. Even the supermassive black holes that anchor these cosmic islands will eventually dissolve into radiation, their immense gravitational power fading like whispers in the void. All things in our universe exist in cycles of transformation. Matter becomes energy. Energy allows for the formation of matter. The hydrogen forged in the earliest moments after the Big Bang fuels the stars that create heavier elements. Those elements scatter when stars die, seeding the cosmos with the building blocks of planets, of moons, of comets, and of life itself. We are, as the poets and scientists both remind us, made of stardust. What makes our moment in cosmic time remarkable is not its permanence, but its rarity. We exist in an era when stars still shine, when galaxies still form, when energy flows freely between states. This cosmic springtime will not last forever. The universe ages just as we do, though on timescales beyond human comprehension. Perhaps there is wisdom in this recognition. By understanding the temporary nature of stars and galaxies, we gain perspective on our own brief lives. We learn to value the moment we inhabit, this extraordinary window when conscious beings can look up at the night sky and wonder at the light that reaches us from distant suns. The fading of galaxies is not a tragedy, but a natural progression, a change as inevitable as the seasons. And just as winter has its own stark beauty, there is a certain elegance in the universe's long transition to darkness. The slow dance of dead stars, the patient evaporation of black holes, the occasional quantum flicker in the void. These processes carry their own strange grace, unfolding with a precision that reflects the fundamental laws of physics. As you rest beneath the canopy of stars visible from Earth, consider that you are witnessing a cosmic moment that will not come again. The particular arrangement of galaxies we observe, the specific stars that form constellations in our sky, these are unique to our time. Future observers, trillions of years hence, would see a different cosmos, one darker and more dispersed. Yet even in that distant future, the echoes of creation would remain. The laws of physics that govern the behavior of matter and energy would continue to operate. The fundamental constants that seem so perfectly tuned for complexity would still hold. The universe would remember its youth in the distribution of its fading remnants, in the trajectory of its expansion, in the subtle radiation that permeates the void. There is comfort in cycles, in patterns that repeat. Day follows night follows day. Seasons turn, years pass. Stars are born, live and die. Galaxies form, evolve and fade. Perhaps the universe itself follows some grander cycle we cannot yet perceive. Or perhaps it simply changes form, trading the brilliant complexity of its youth for the serene simplicity of its maturity. Whatever awaits in the far future, we are privileged to witness the cosmos in its prime. We see light that has traveled across billions of light years to reach our eyes. We observe galaxies in all stages of their evolution. We detect the afterglow of the Big Bang itself. We stand at a unique vantage point in cosmic history, able to look both backward and forward in time. As our journey together concludes, carry with you this perspective. The stars above you are ancient but not eternal. The light they cast has traveled years to reach you. The elements in your body were forged in their fiery hearts. You are connected to this vast cosmic drama, a conscious participant in the universe observing itself, into the long twilight of the cosmos. Their stars dim, their voices fade, but their legacy glows eternal in our dreams. Sleep now, beneath a sky full of memories. The universe watches over you, still and silent. Galaxies aren't static sculptures frozen in the cosmos. They are dynamic, evolving systems that change dramatically over billions of years. Like living organisms, they're born, they grow, they mature, and eventually they age. Understanding this cosmic life cycle helps us comprehend why star formation ultimately ceases. In the early universe, about 13 billion years ago, the first galaxies were chaotic collections of gas and newly formed stars. They were relatively small, often irregular in shape, and bursting with the blue light of massive, short-lived stars. These infant galaxies were prodigious star formers, converting their abundant gas reserves into stellar nurseries at remarkable rates. We can see these youthful galaxies in our deepest telescope observations, looking back through time at the ancient cosmos. Their light, traveling for billions of years across expanding space, reveals compact systems ablaze with new stars. The James Webb Space Telescope has revealed these cosmic toddlers in unprecedented detail, showing us the universe's first stellar generations. As galaxies mature, they often develop more organized structures. Many form the familiar spiral pattern we associate with our own Milky Way. These spiral arms aren't solid structures, but rather density waves, like ripples moving through the galactic disk. As gas clouds pass through these density waves, they're compressed, triggering bursts of star formation. This is why spiral arms often appear blue. They're illuminated by the light of massive, newly formed stars that shine with an intense blue-white glow. Other galaxies evolve into different forms. Some become lenticular galaxies, disc-shaped like spirals, but lacking the dramatic arms. Others transform into elliptical galaxies, rounded or football-shaped collections of stars with little gas and minimal new star formation. This diversity of galactic shapes isn't merely aesthetic. It tells us about their different evolutionary paths and star-forming histories. Spiral galaxies are typically active star formers, their gas-rich disks continuously birthing new stars. Elliptical galaxies, by contrast, have largely exhausted their star-forming potential, home to older stellar populations that glow with a softer, redder light. What drives these transformations? One of the most dramatic forces shaping galactic evolution is galactic mergers, collisions between galaxies drawn together by gravity's inexorable pull. When two spiral galaxies merge, the result is cosmic chaos. Their beautiful, ordered structures are disrupted, gas clouds collide, and a spectacular burst of star formation often follows. For a relatively brief period, perhaps a few 100 million years, the merging system may shine brilliantly with the light of newly formed stars. Astronomers call these starburst galaxies, and they represent some of the most luminous objects in the universe. But this frenzy of star formation eventually consumes much of the available gas, leaving behind an elliptical galaxy filled primarily with aging stars. The merger transforms two gas-rich, star-forming spirals into a single gas-poor elliptical where few new stars are born. It's a cosmic transformation from youth to middle age. We can observe these mergers in various stages throughout the universe. Some galaxies are just beginning their gravitational dance, their outer regions stretching toward each other like cosmic hands reaching across space. Others are in the midst of violent collision, their stars and gas clouds passing through each other in a spectacular interaction that may last hundreds of millions of years. Still others show the aftermath, distorted shapes, tidal tails of stars and gas flung into intergalactic space, and the intense starbursts that often accompany these cosmic crashes. Not all galaxies experience dramatic mergers, however. Some evolve more quietly, gradually depleting their gas reserves through steady star formation. Others have their star-forming potential gently extinguished by more subtle processes. The path a galaxy takes depends greatly on its environment and its history. Galaxies in dense clusters often age more rapidly than their isolated counterparts. Surrounded by numerous neighbors in a relatively confined space, they're subject to frequent interactions that can strip away their gas. The hot, diffuse gas that fills the space between cluster galaxies, the intracluster medium, can scrub away the cold gas needed for star formation as galaxies move through it, like rain stripping leaves from a tree during a storm. Isolated galaxies, floating alone in cosmic voids, may retain their star-forming capabilities much longer. With no neighbors to disturb them and no harsh cluster environment to strip away their gas, they can maintain steady star formation for billions of years longer than their clustered counterparts. The presence of a supermassive black hole at a galaxy's center also influences its evolution. All large galaxies harbor these cosmic titans, with masses millions or billions of times that of our Sun. When these black holes actively feed on surrounding material, they become what astronomers call active galactic nuclei, or AGN. The energy released from these feeding black holes can heat surrounding gas, driving it away from the galaxy and effectively shutting down star formation. This process, known as AGN feedback, represents one of the most significant ways galaxies can be quenched, their star formation halted or significantly reduced. The black hole, while comprising a tiny fraction of the galaxy's mass, wields enormous influence over the fate of the entire system. The life cycle of galaxies is also influenced by more gradual processes. As stars form and evolve, they return material to the interstellar medium through stellar winds and eventual death. Massive stars end their lives in spectacular supernovae, enriching surrounding gas with heavy elements, the carbon, oxygen, nitrogen, and other elements essential for planets and life. This enriched gas is then incorporated into new generations of stars. Astronomers can observe this progression through what they call metallicity, the abundance of elements heavier than hydrogen and helium. Young galaxies show low metallicity, while older, more evolved galaxies contain stars richer in heavy elements, evidence of multiple generations of stellar birth, life, and death. As time passes, galaxies gradually transition from primarily blue, indicating active star formation, to primarily red, indicating aging stellar populations. This blue to red evolution marks the most significant transition in a galaxy's life cycle, the slow winding down of its star-forming capacity. The cosmic conveyor belt of stars continues, but at an ever-slowing pace. New stars become increasingly rare, while existing stars gradually age. Blue giants burn out, leaving behind red giants, white dwarfs, neutron stars, and black holes. The galaxy's light shifts toward the red end of the spectrum, not from movement, but from the changing stellar population itself. This aging process doesn't occur uniformly across all galaxies or even within individual galaxies. Some regions continue forming stars while others have already gone quiet. Our own Milky Way exhibits this patchwork quality. Vigorous star formation continues in spiral arms and the galactic center, while other regions have grown relatively quiescent. For most large galaxies in our universe today, this aging process is well underway. The cosmic peak of star formation, the era when stars were being born at the highest rate across the universe, occurred roughly 10 billion years ago. Since then, the overall star formation rate has declined, and many once vigorous galaxies have grown quiet. It's important to note that this doesn't mean galaxies are dying in any traditional sense. Even without new star formation, existing stars continue to shine for billions or trillions of years, depending on their mass. The smallest, most common stars, red dwarfs, burn their fuel so efficiently they can shine for trillions of years, far longer than the current age of the universe. So while galaxies may stop forming new stars, they remain vibrant collections of existing stars for unimaginably long timescales. Their light continues to shine, just with a different character, the soft red glow of mature stellar populations rather than the brilliant blue of stellar youth. As galaxies age, their evolution slows. Changes that once occurred over millions of years now take billions. The dramatic transformations of youth give way to the more subtle changes of maturity. Like ancient trees that still stand but no longer produce new growth, these galaxies maintain their grandeur while slowly, imperceptibly fading. As we observe galaxies at different stages of this grand cosmic cycle, we're seeing snapshots of what was, what is, and what will be. Young blue galaxies show us our own Milky Way's distant past. Red quiescent galaxies reveal its likely future. The universe provides us with a vast cosmic laboratory where the full life cycle of galaxies plays out across space and time, and fewer stars emerge from the void. In the language of astronomy, a galaxy that stops forming stars is said to be quenched. This evocative term brings to mind a flame being extinguished, light fading to darkness. The reality of galactic quenching is equally poetic, but unfolds over billions of years, a slow dimming rather than a sudden darkening. What does it truly mean for a galaxy to run out of stars? It's not that existing stars vanish. They continue shining for billions or even trillions of years. Rather, it means the galaxy loses its ability to form new stars. The cosmic cradles go empty. The stellar nurseries close their doors. The galaxy continues to exist, populated by its aging stellar citizens, but no new stellar lives begin. This process, the transition from actively star-forming to quiescent, is one of the most significant events in galactic evolution. Astronomers have devoted considerable effort to understanding how and why galaxies quench, observing systems caught in different stages of this transition, and developing sophisticated models to explain their observations. To form stars, a galaxy needs cold, dense gas, primarily molecular hydrogen. Anything that removes this gas, heats it, or prevents it from cooling and condensing can contribute to quenching. Several mechanisms drive this process, sometimes working in concert, sometimes independently. One of the most straightforward paths to quenching is simply running out of gas. Galaxies don't have an infinite supply of star-forming material. They begin with a finite amount of gas, and as they convert this gas into stars over billions of years, their reserves gradually deplete. This process, sometimes called starvation, is a slow, natural end to a galaxy's star-forming life. Imagine a baker who can no longer make bread because flour is no longer available. The baker hasn't forgotten how to bake, but without the essential ingredient, no new loaves can be produced. Similarly, a galaxy without cold gas cannot form new stars, no matter how ideal its other conditions might be. For many galaxies, however, the story is more complex. They don't simply exhaust their gas through star formation. Their gas is actively removed or rendered unsuitable for stellar birth. When galaxies move through the hot, diffuse gas that fills galaxy clusters, the intracluster medium, they experience a form of cosmic headwind. This pressure can be strong enough to push gas out of galaxies, particularly from their outer regions, where gravitational binding is weaker. Like a strong wind stripping leaves from a tree, ram pressure strips away the lifeblood of star formation. We can observe this process directly in some nearby galaxy clusters. Telescopes have captured stunning images of galaxies with long tails of gas stretching behind them as they move through cluster environments, clear evidence of their gas being stripped away by this cosmic wind. These galaxies leave behind trails of the very material from which stars would otherwise form, like ships leaving wakes in a cosmic ocean. In dense environments, galaxies frequently experience close encounters with neighbors. While not direct collisions, these near misses create gravitational disturbances that can strip away gas, disrupt gas clouds, or trigger bursts of star formation that quickly deplete gas reserves. Imagine walking through a crowded room where people occasionally bump into you. A single bump might have little effect, but repeated jostling from all directions would eventually take its toll. Similarly, repeated gravitational interactions can gradually transform a gas-rich, star-forming galaxy into a gas-poor quiescent one. While these external mechanisms are important, particularly in dense environments, galaxies can also quench from within. One of the most significant internal quenching mechanisms involves the supermassive black holes that reside at the centers of nearly all large galaxies. These cosmic behemoths, despite making up a tiny fraction of their host galaxy's mass, can wield enormous influence over galactic evolution. When material falls into a supermassive black hole, it doesn't do so quietly. The infalling gas forms an accretion disk, a swirling maelstrom of matter heated to millions of degrees. This process releases tremendous energy in the form of radiation, particle jets, and outflows. This energetic output from what astronomers call an active galactic nucleus, or AGN, can heat the surrounding gas, preventing it from cooling and collapsing to form stars. It can also drive powerful outflows that expel gas from the galaxy entirely. The black hole, in essence, acts as a thermostat, regulating or even terminating star formation throughout the galaxy. The relationship between supermassive black holes and their host galaxies is complex and bidirectional. The galaxy feeds the black hole, and in turn, the black hole influences the galaxy's evolution. This cosmic feedback loop plays a crucial role in determining when and how quickly a galaxy quenches. Observational evidence for this AGN feedback comes in many forms. Astronomers observe massive outflows of gas from galaxies with active nuclei, sometimes extending tens of thousands of light years. They detect hot gas bubbles inflated by the energy from central black holes. They see correlations between black hole activity and reduced star formation. Together, these observations paint a compelling picture of how these central engines contribute to galactic quenching. Even without an active nucleus, the central regions of galaxies can develop structures that limit star formation. Many spiral galaxies, including our own Milky Way, develop bars-elongated structures of stars that cut across their centers. These bars can funnel gas inward toward the galactic center, depleting the outer regions of star-forming material. Additionally, the buildup of a dense central bulge of stars can stabilize gas against the collapse necessary for star formation. Gas clouds need to reach a critical density to begin forming stars, and in regions with certain dynamics or stellar densities, this collapse can be inhibited. Massive stars produce intense radiation and powerful stellar winds that can disperse surrounding gas. When these stars explode as supernovae, they inject tremendous energy into their surroundings, potentially heating gas or even expelling it from the galaxy. This process creates a self-regulating system. Star formation produces massive stars, which then restrict further star formation in their vicinity. In smaller galaxies with weaker gravitational fields, this stellar feedback can be powerful enough to eject significant amounts of gas, effectively shutting down star formation across the entire galaxy. The collective effect of many supernovae can create what astronomers call a galactic wind, a large-scale outflow of gas driven by the combined energy of stellar explosions. These winds, detected in many star-forming galaxies, carry away material that might otherwise form future generations of stars. It's important to understand that quenching isn't always an all-or-nothing process. Many galaxies experience reduced, rather than completely halted star formation. Others quench in some regions while continuing to form stars elsewhere. Some experience multiple episodes of quenching and rejuvenation as they acquire new gas through mergers or accretion from the intergalactic medium. The spatial pattern of quenching within galaxies provides important clues about the underlying mechanisms. Some galaxies quench from the inside out, with star formation ceasing first in central regions and then gradually in outer regions. This pattern often indicates internal processes like AGN feedback or bulge stabilization. Other galaxies quench from the outside in, with star formation continuing in central regions after it has ceased in the outskirts. This pattern typically suggests external processes like ram pressure stripping, which affects outer regions first, or starvation, which impacts lower density regions more quickly. By studying these patterns across large samples of galaxies, astronomers can determine which quenching mechanisms dominate in different environments and for different galaxy types. The picture that emerges is complex. There is no single path to quiescence, but rather multiple routes that galaxies may follow. The timing of quenching also varies dramatically. Some galaxies quench rapidly, transitioning from actively star-forming to quiescent in less than 1 billion years, quick by cosmic standards. Others undergo a much more gradual decline, their star formations slowly dwindling over many billions of years. This creates what astronomers call the green valley, a transitional space between the actively star-forming blue cloud and the quiescent red sequence in galaxy classification schemes. Galaxies in the green valley are caught in the act of quenching, offering astronomers a glimpse of this critical transition. The mass of a galaxy plays a crucial role in determining its quenching timeline. A striking observation in modern astronomy is that massive galaxies tend to quench earlier and more completely than their lower mass counterparts. This phenomenon, known as mass quenching, suggests that internal processes become increasingly important as galaxy mass increases. This pattern makes sense when we consider the deeper gravitational wells of massive galaxies. Their stronger gravity makes it harder for stellar feedback or external processes to remove gas. However, their more massive central black holes can generate more powerful AGN feedback, potentially providing the necessary force to overcome even their substantial gravitational binding. The universe itself contributes to quenching through its ongoing expansion. In the early universe, galaxies were closer together, and the cosmic gas was denser and more easily accreted. As space expands, the gas between galaxies becomes more diffuse and harder to capture. This cosmic starvation gradually reduces the supply of fresh gas available to feed ongoing star formation. For galaxies that have already quenched, there can occasionally be second acts. A merger with a gas-rich companion can provide fresh fuel, temporarily rejuvenating star formation. Cool streams of gas from the cosmic web, the filamentary structure that connects galaxies across the universe, can sometimes provide a new supply of star-forming material. However, these rejuvenation events become increasingly rare as the universe ages. The overall trend points toward a gradually quieting cosmos, with fewer and fewer galaxies maintaining active star formation. The quenching of star formation impacts more than just the visible appearance of galaxies. It affects their overall evolution, their interactions with surroundings, and even their ultimate fate. A quenched galaxy evolves differently than an active one, following a quieter, more gradual path of change. When we observe distant quenched galaxies, we're seeing systems that ceased forming stars billions of years ago. Their stars have continued aging since that time, their light shifting further toward the red end of the spectrum, as hotter, bluer stars exhaust their fuel, and cooler, redder stars come to dominate the galaxy's light. What's particularly fascinating is that we can now observe galaxies that quenched when the universe was just a few billion years old. These remarkably early quenched systems challenge our understanding of galactic evolution, suggesting that powerful quenching mechanisms were already operating in the young cosmos. The James Webb Space Telescope has revealed some of these ancient quenched galaxies in unprecedented detail, showing us mature, red systems existing when the universe was less than a quarter of its current age. Their presence requires us to refine our models of how quickly galaxies can form, evolve, and ultimately cease star formation. As we contemplate the quenching process, it's worth reflecting on our own galaxy's future. The Milky Way continues to form stars at a modest rate, roughly 1 to 2 solar masses per year. It still harbors significant reserves of gas, particularly in its outer regions, yet it too will eventually quench. Current models suggest that our galaxy's star formation will gradually decline over the next few billion years, potentially accelerated by our upcoming collision with the Andromeda Galaxy approximately 4 billion years from now. This collision will likely trigger a starburst phase, a period of intense star formation, followed by quenching as the merged system settles into an elliptical shape with depleted gas reserves. The quenching of galaxies represents a fundamental transition in cosmic evolution, a shift from an era dominated by stellar birth and growth to one characterized by stellar aging and quiescence. It's not the end of galactic history, but rather the beginning of a new, quieter chapter, one that will last far longer than the star-forming phase that preceded it. As we observe galaxies across the spectrum of quenching, from those just beginning to show signs of reduced star formation to those that quenched billions of years ago, we're witnessing one of the most significant processes in cosmic evolution. The gradual silencing of stellar nurseries, the slow transition from cosmic youth to cosmic maturity. Slowly, like embers cooling in the dark, galaxies fade from creation into quiet. To truly understand why galaxies stop forming stars, we must look beyond the visible. The fate of galaxies is shaped not only by what we can see, stars, gas, and dust, but also by what remains invisible to our eyes, dark matter and the cosmic environment. Dark matter, though unseen, makes up roughly 85% of all matter in the universe. It emits no light, absorbs no light, yet its gravitational influence is unmistakable. Every galaxy we observe sits within a much larger halo of this mysterious substance, like islands rising from an invisible sea. These dark matter halos formed first in the early universe, creating gravitational wells into which ordinary matter, what astronomers call baryonic matter, could flow. Gas followed the gravitational pull of dark matter, pooling in these cosmic depressions, eventually becoming dense enough to form the first stars and galaxies. The relationship between a galaxy and its dark matter halo is fundamental to its evolution. The halo acts as both cradle and cage, nurturing the galaxy's formation while constraining its future development. The size, shape, and density profile of a dark matter halo influence nearly every aspect of its resident galaxy, including its star formation history and ultimate quenching. One critical way dark matter halos affect star formation is through their role in gas accretion. Galaxies, particularly in their youth, grow by acquiring gas from the surrounding intergalactic medium. This gas follows cosmic filaments, the vast threads of the cosmic web that connect galaxies across millions of light years, eventually falling into dark matter halos. The rate at which galaxies can acquire this fresh gas depends significantly on their halo properties. More massive halos, with their stronger gravitational pull, can more effectively draw in gas from their surroundings. This helps explain why galaxies in more massive halos typically form stars more vigorously in the early universe. They simply had better access to the raw materials of star formation. However, this relationship changes as the universe evolves. Past a certain mass threshold, roughly equivalent to the dark matter halo of our Milky Way, a phenomenon called hot mode accretion begins to dominate. Gas falling into these massive halos becomes shock-heated to temperatures of millions of degrees, creating a barrier of hot gas that surrounds the galaxy. This hot gas cannot immediately form stars. It must first cool, a process that can take billions of years in these environments. The result is a galaxy surrounded by a reservoir of gas that is temporarily unavailable for star formation. The dark matter halo, once an ally in gathering star-forming material, becomes an impediment to its use. In the most massive halos, those hosting galaxy clusters, this effect becomes even more pronounced. These environments contain gas heated to tens of millions of degrees, forming what astronomers call the intracluster medium. This superhot plasma effectively cuts off cluster galaxies from the cold gas streams that might otherwise sustain their star formation. Beyond their effects on gas accretion, dark matter halos also influence galaxy mergers, another key factor in star formation quenching. The frequency and nature of galaxy mergers depend on the properties of their respective dark matter halos. Massive halos are more likely to attract and absorb smaller halos along with their resident galaxies, leading to more frequent mergers. The dark matter halo of a galaxy also determines which cosmic environment it will inhabit. Galaxies reside in a diverse array of environments, from the dense cores of galaxy clusters to the relative solitude of cosmic voids. These environments exert profound influence over galactic evolution and star formation. In the densest environments, galaxy clusters, several environmental processes act to quench star formation. We've already discussed ram pressure stripping, where the motion of a galaxy through the intracluster medium strips away its gas. This process is particularly effective at removing gas from the outer regions of galaxies, where the gravitational binding is weaker. Direct observations reveal galaxies with long tails of gas streaming behind them as they plow through cluster environments, vivid evidence of this stripping in action. Over time, these galaxies lose more and more of their gas, gradually strangling their ability to form new stars. Another important environmental process is galaxy harassment, repeated high-speed encounters between galaxies in dense environments. While not as dramatic as full mergers, these interactions can significantly disturb gas distributions, trigger central gas inflows, and accelerate gas consumption through induced star formation. Imagine a galaxy repeatedly jostled by passing neighbors. Each encounter disrupts its delicate structure a little more, eventually transforming it from a well-ordered, gas-rich system to a disturbed, gas-poor one. This death, by 1,000 cuts, gradually diminishes the galaxy's star-forming potential. Even before galaxies enter these dense environments, they may experience pre-processing in smaller groups. As galaxies fall into clusters, they often do so as members of galaxy groups, smaller collections of galaxies bound together by gravity. Within these groups, gentler versions of environmental processes begin the quenching process, so that many galaxies are already transitioning to quiescence before they reach cluster centers. The contrast between clustered and isolated galaxies is striking. Isolated galaxies, those far from dense environments, typically retain their gas and continue forming stars for much longer than their clustered counterparts. Without external processes to remove their gas or disrupt their structure, these cosmic hermits can maintain star formation for many additional billions of years. Some of the most isolated galaxies in our universe reside in cosmic voids, vast regions of relative emptiness between the filaments of the cosmic web. These void galaxies tend to be smaller, bluer, and more gas-rich than galaxies of similar mass in denser environments. Their isolation has preserved their youth, allowing them to continue forming stars, while their clustered counterparts have long since gone quiet. Between the extremes of dense clusters and empty voids lies the cosmic web itself, the network of filaments and sheets that forms the large-scale structure of our universe. Galaxies residing along these filaments experience an intermediate environment, neither as harsh as clusters nor as gentle as voids. The properties of dark matter halos and environments evolve over cosmic time, creating changing conditions for star formation. In the early universe, gas was more abundant and filamentary accretion more efficient. Galaxies could more readily acquire fresh gas to fuel ongoing star formation. As the universe expanded and evolved, several changes occurred that made it increasingly difficult for galaxies to maintain star formation. The overall density of the universe decreased, making gas accretion less efficient. Galaxy environments matured, with clusters growing larger and environmental effects becoming more pronounced. Within this evolving cosmic context, an individual galaxy's fate depends greatly on its specific journey through the cosmic web. Two galaxies of identical mass can experience vastly different star formation histories based solely on their environmental trajectories. Consider two similar galaxies that formed 13 billion years ago. One remains relatively isolated, perhaps moving along a less populated filament of the cosmic web. It continues forming stars at a modest but steady rate, its blue spiral arms still actively creating new stellar life even today. The other falls into a forming galaxy cluster 10 billion years ago. Subjected to ram pressure stripping, harassment, and pre-processing, it loses its gas reservoir and stops forming stars. By today, it has become a red, featureless elliptical galaxy, its star-forming days long behind it. Galaxies tend to exhibit similar properties to their neighbors, particularly regarding star formation activity. Regions of the universe with one quenched galaxy are likely to contain others, while regions with one actively star-forming galaxy typically host others in similar states. This conformity extends beyond obvious dense clusters into the so-called group environment. smaller collections of galaxies bound together by gravity. Even in these less extreme environments, we observe galaxies influencing one another's evolution through subtle gravitational interactions and shared environmental conditions. All these effects, from dark matter halo properties to environmental processes, create what astronomers call galaxy ecology. Just as terrestrial ecology studies the relationships between organisms and their environment, galaxy ecology examines how cosmic surroundings shape galactic evolution. This ecological perspective provides a richer understanding of why galaxies stop forming stars. A galaxy's fate isn't determined solely by its internal properties, but by its complex relationships with surrounding gas, neighboring galaxies, and the underlying dark matter structure, all evolving together through cosmic time. As we contemplate this cosmic ecology, we gain a deeper appreciation for the forces shaping our own Milky Way. Our galaxy resides in a moderately massive dark matter halo, on the edge of where hot mode accretion begins to dominate. It sits within the Local Group, a small collection of galaxies dominated by ourselves and the Andromeda Galaxy, which itself moves along a filament of the cosmic web. This particular ecological niche has allowed our galaxy to maintain steady star formation for billions of years, creating the conditions that ultimately led to our existence. Yet even the Milky Way will eventually succumb to the forces of quenching, either through the slow depletion of its gas reserves or through its upcoming merger with Andromeda. When we observe distant galaxies caught in different stages of quenching, we're witnessing the diverse outcomes possible within this complex cosmic ecology. Some galaxies quickly succumb to harsh environments, while others maintain their youthful star formation for much longer periods. Invisible threads tug at galaxies, shaping their fate, pulling them through environments that strip them of breath. When a galaxy has largely ceased forming new stars, astronomers sometimes use a stark phrase to describe it: red and dead. This evocative terminology captures the fundamental transformation these systems have undergone, from vibrant blue, star-forming galaxies to redder systems where stellar birth has slowed to a trickle or stopped entirely. The most obvious feature of quenched galaxies is their color. Active star-forming galaxies appear distinctly blue, their light dominated by massive, hot, short-lived stars that shine with an intense blue-white glow. When star formation ceases, these massive blue stars are the first to disappear. Without new stars being born to replace them, galaxies gradually shift toward the red end of the spectrum, their light increasingly dominated by smaller, cooler, longer-lived stars. The shift from blue to red doesn't happen instantaneously. Galaxies in the process of quenching often appear green in false-color astronomical images, not because they actually emit green light, but because they have an intermediate color profile. Astronomers refer to these transitional objects as green valley galaxies, caught in the act of shutting down their star formation. Beyond color, quenched galaxies often exhibit distinct structural characteristics. Star-forming galaxies typically have well-defined structures, the beautiful spiral arms of galaxies like our Milky Way, or the irregular but detailed structures of smaller systems. In contrast, quenched galaxies tend towards simpler, smoother structures. Many take on an elliptical shape, rounded or football-like distributions of stars with little internal structure. Others become lenticular, maintaining a disc-like shape but losing their spiral arms and detailed features. Some of the most massive quenched galaxies are giant ellipticals, enormous collections of stars that can span more than 1 million light-years across. These cosmic titans often reside at the centers of galaxy clusters. Their current form the end result of multiple mergers between previously distinct galaxies. Their smooth, featureless appearance belies a complex assembly history. At the other extreme are much smaller quenched systems, dwarf elliptical galaxies that contain just a fraction of the stars found in systems like our Milky Way. These diminutive galaxies often orbit larger neighbors, their star formation potentially cut short by interactions with their more massive companions. One striking observation about quenched galaxies is their prevalence in the centers of galaxy clusters. These dense environments host many of the most massive, most thoroughly quenched galaxies in our universe. The centers of rich clusters are dominated by red, elliptical systems, while blue, star-forming galaxies become increasingly common only as one moves toward the cluster outskirts. When astronomers look back in time by observing very distant galaxies, they find that this pattern was less pronounced in the early universe. In young galaxy clusters, blue star-forming galaxies were more common even in central regions. This tells us that the environmental quenching processes take time to transform cluster populations. Another fascinating aspect of quenched galaxies is their size evolution through cosmic time. Very distant quenched galaxies, those that cease star formation in the early universe, are often much more compact than similarly massive quenched galaxies in the nearby universe. Over time, these compact systems appear to grow in size, primarily through dry mergers, collisions with other already quenched galaxies. The stellar populations within quenched galaxies tell us much about their histories. By studying the distributions of stellar ages, astronomers can reconstruct the star formation histories of these systems. When they formed most of their stars, how quickly they quenched, and whether they experienced multiple episodes of star formation before finally falling silent. The most distant quenched galaxies yet observed existed when the universe was less than 3 billion years old, surprising astronomers with how quickly some galaxies can form their stars and subsequently cease star formation. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, has revealed these ancient quenched galaxies in new detail. As we observe quenched galaxies across different cosmic epochs, we're seeing different stages in the universe's gradual transition from predominantly star-forming to increasingly quiescent. This cosmic transition isn't uniform across all environments or galaxy masses. The most massive galaxies typically quenched first, with the transition to quiescence gradually extending to lower mass systems over time. Similarly, dense environments like galaxy clusters quenched earlier and more thoroughly than less dense regions of the cosmic web. The result is our current universe, where both star-forming and quenched galaxies coexist, their relative proportions varying with environment and galaxy mass. This mixed population represents a snapshot of an ongoing cosmic transition, the gradual shift from an era dominated by stellar birth to one increasingly characterized by stellar aging. What does the future hold for these quenched galaxies? For the most part, they will continue their quiet evolution, their stars gradually aging, their color slowly reddening further as hotter stars exhaust their fuel and cooler stars come to dominate. Occasional mergers will alter their shapes and sizes, but without significantly changing their quiescent nature. These quenched galaxies also offer a preview of our own galaxy's distant future. Its spiral arms will have faded, its blue stellar nurseries gone quiet, its appearance transformed from a vibrant spiral to a more uniform elliptical shape. Even in this quiescent state, however, our galaxy will continue to exist, its stars shining on for billions or trillions of years, gradually cooling, but never truly dying. Like all quenched galaxies, it will transition not to non-existence, but to a different mode of being, quieter, redder, more stable, but still very much a galaxy. With time, even the brightest galaxies grow dim, bathed in the soft red of ancient stars, no longer forming, only aging. To understand the gradual quieting of galaxies, we must understand the individual lives of their stellar inhabitants. Stars are not eternal, they are born, they live, and eventually they die. This cosmic life cycle, multiplied across billions of stars, shapes the evolution of entire galaxies. Each star begins as a condensation within a vast cloud of gas and dust. Gravity draws this material inward, compressing it and heating it until nuclear fusion ignites in the core. This moment marks the true birth of a star, the beginning of a long, steady burning that will define most of its existence. From this common beginning, stars follow remarkably different paths. Their mass at birth largely determines their destiny, the brightness they will achieve, how long they will shine, and how they will eventually end their days. The most common stars in our universe are red dwarfs, small, cool stars with less than half the mass of our Sun. These cosmic embers burn their fuel with remarkable efficiency, maintaining a steady, modest glow for incredible spans of time. The smallest red dwarfs may shine for more than 1 trillion years, nearly 100 times the current age of the universe. Stars like our Sun, which astronomers categorize as G-type main sequence stars, are less common but more luminous. With lifespans of about 10 billion years, they represent a middle ground in the stellar population, neither particularly short-lived nor exceptionally long-lasting. More massive stars burn much brighter but exhaust their fuel far more quickly. A star with 10 times the mass of our Sun might shine more than 1,000 times brighter, but it will last only a few tens of millions of years, a mere cosmic moment compared to the billions or trillions of years smaller stars endure. This diversity of stellar lifespans creates a natural evolution in a galaxy's light. When a generation of stars forms, the massive, brilliant stars dominate the galaxy's appearance initially. Their intense blue-white light gives young star-forming regions their characteristic color. But these stellar giants quickly burn through their fuel, leaving the longer-lived, less massive stars to shine on. Stars don't simply fade away when their fuel is exhausted. Their deaths are often as varied and noteworthy as their lives, and these stellar endings play crucial roles in galactic evolution. For stars similar to or smaller than our Sun, the end comes relatively gently. As hydrogen in the core is depleted, the star expands into a red giant. Eventually, the star sheds its outer layers, creating a beautiful planetary nebula, an expanding shell of glowing gas that dissipates into the interstellar medium. What remains is a white dwarf, the hot, dense core of the former star, roughly Earth-sized, but containing up to 1.4 times the mass of our Sun. This stellar remnant simply cools, gradually radiating away its heat over many billions of years. For stars substantially more massive than our Sun, the end is more dramatic. When a massive star exhausts its core fuel, it begins fusing heavier elements in a series of stages, each burning hotter and faster than the last. This progression continues until the star develops an iron core. The core collapses in less than a second, triggering a catastrophic explosion, a supernova, that for a brief period may outshine an entire galaxy. Outer layers of the star are blasted into space, creating an expanding shell of hot gas enriched with all the elements the star created during its lifetime. Meanwhile, the core may collapse into a neutron star, or if massive enough, form a black hole. These stellar deaths, particularly supernovae, play crucial roles in galactic evolution. They spread newly formed heavy elements throughout the galaxy, enriching the interstellar medium with the building blocks necessary for planets and eventually life. Iron in your blood, calcium in your bones, the oxygen you breathe, all were forged in the hearts of stars and scattered by their explosive deaths. Supernovae also inject tremendous energy into their surroundings, creating shock waves that compress nearby gas clouds and potentially trigger new episodes of star formation. This creates a cycle where stellar deaths can lead to stellar births, a cosmic circle of life playing out across galactic scales. But there's another side to this energetic feedback. The combined effect of many supernovae can disrupt and heat the interstellar medium, making it harder for gas to cool and collapse into new stars. This supernova feedback represents one way that star formation might be suppressed, particularly in low-mass galaxies. As star formation in a galaxy slows or ceases, this recycling process gradually winds down. Fewer massive stars form, leading to fewer supernovae, which means less energetic stirring of the interstellar medium and less enrichment with heavy elements. The galaxy transitions to a quieter phase, dominated by the steady burning of long-lived stars, rather than the dramatic births and deaths of massive ones. In a fully quenched galaxy, the stellar life cycle continues, but in an increasingly limited way. Without new star formation, the population gradually ages. Massive stars disappear entirely as the last examples exhaust their fuel and explode. The galaxy grows redder as its light becomes dominated by smaller, cooler stars and the white dwarfs left behind by intermediate mass stars. Over even longer timescales, hundreds of billions or trillions of years, the smallest red dwarf stars will begin to exhaust their fuel. One by one, these tiny stars will swell slightly, then shrink to become white dwarfs. Eventually, a quenched galaxy will consist primarily of stellar remnants, white dwarfs, neutron stars, and black holes, with perhaps a few of the smallest red dwarfs still slowly burning. It's not that stars suddenly disappear, but rather that the balance shifts from a mixture of stellar births, lives, and deaths to a population dominated by quiet, steady burning and slow cooling. The brilliant blue giants fade away, the spectacular supernovae become increasingly rare, and the galaxy settles into a long, quiet twilight. Even death cannot birth anew. The galaxy grows still,